In this video, we'll cover the mole. When you go to a donut shop and you ask for 1 dozen of donuts, how many donuts do you receive? For every 1 dozen, you receive 12 donuts. Well, if you ask for 1 dozen, say at the market, of eggs, then you get 12 eggs. So the word dozen refers to how many in that package contains, right? If you were to say, think about a pair of something, may I see a pair of socks? And how many socks would you take out? So 1 pair would equal to 2 of something socks. If I ask for a pair of pencils, then I'm asking for 2 pencils total. Century, if you think about century of years, 1 century refers to 100 years, right? So that one of something refers to this many years, socks, eggs, donuts, calculator, pencils, right? And that goes same for mole. 1 mole, say I want 1 mole of donuts. Okay, how many donuts will you get? You will get very many. In fact, you would get 6.022 times 10 to the 23. If I were to stretch it out in a standard form, you would have just a little too many. I will see if I could have enough zeros there to cover it all. Let's see, 1, 2, 3, 4, 6, 8, 13, 14, 15, 16, 17, 18, 19, 20, 21, 23. So that's how many zeros I would need, and that's how much donuts I would receive if I ask for 1 mole of donuts. This number, 6.022 times 10 to the positive 23, or this giant number, we call this an Avogadro's number. Avogadro's number. And instead of saying the whole thing, we just say 1 mole of that particular element or whatever you're looking for. So let's go a little bit further into Avogadro's number and look at some images that is associated with it. All of these elements here refers to 1 mole of that particular element. For example, look at aluminum. If I were to count every aluminum there are in this petri dish, and then I would be counting 6.022 times 23rd aluminum. If I were to count every bits of atom here of iron, then that's same thing. I would get the Avogadro's number. So it's nicely put here. Something important to note, based on what we have learned so far, is that an equality comes forth based on what I have discussed. Remember, 1 mole of anything, it doesn't matter what it is equal to 6.022 times 10 to the 23 atoms, molecule, formula units, ions, pencils, hair strands, boxes, what have you, right? Every 1 mole of that is equal to that Avogadro's number. Because there's an equal sign in between, we could come up with the conversion factor, or also known as the fraction form. And where we have 1 mole on top and the 6.022 times 10 to 23 of whatever we're looking for on the bottom. Or we could have that Avogadro number on top and 1 mole on the bottom. Having this allows us to do some calculation, mole calculation. So let's do a learning check based on what we learned so far. Here it says cobalt is a metal that is added to steel to improve its resistance to corrosion. Calculate the number of moles in a sample of cobalt containing 5.00 times 10 to the 20 atoms. So what it's essentially asking for is you start off with 5.00 times 10 to the 20 atoms of cobalt, and you want to do some calculation so that in the end I'm left with moles of cobalt, and that's what we're looking for, moles in a sample of cobalt. So there has to be some calculation between that allows you to cancel out atoms, but then moles remain. Remember, 1 mole of anything, and right now we're talking about cobalt, is equal to 6.022 times 10 to the 23 atoms of cobalt. That means the two fraction form or conversion factor could arise from here. One could be where you have 1 mole on top and the Avogadro number on the bottom, or you could have 1 mole on the bottom and you have the Avogadro number on top. Those are two possibilities when it comes to when you look at something is equal to something else. So let's see, which one am I going to use in order for me to cancel out the atom? Hopefully you are able to pick this one. And why am I picking this one? This is because the atom goes on the bottom. You have 1 mole of cobalt on top. Atoms of the cobalt will cancel out since they're in diagonal each other. Anytime they're in diagonal each other, you could cancel the unit out. And you're left with the moles of cobalt. And that's what we want, because that's what we want, moles of cobalt. You notice here on the moles, I put MOL, and over here MOLES. They are the same thing. So let's go ahead and punch this into the calculator. So my calculator, you're going to punch 5.00 times 10 to the 20th. And multiply that by 1. Since over here, the 1 is on top. And then press enter. Then you're going to press the division sign because you need to divide by everything that's on the bottom, and that's right here. The 6.022 times 10 to 23. You're going to open up a parentheses. Make sure all of the values are there. 6.022 times 10 to the 23rd. Okay. Then you're going to close it and then press hit enter. Then my calculator spits out the following: 0.000830289. If you look at the significant figures on the starting value, you see that there is 3. 5.00. Those are all the 3. The times to the 10 to the 20th, they do not count part of the sig figs, nor do the ones with the 1 mole and the Avogadro number, because that's infinite many. And equality is infinite many sig figs. So you look at the problem in itself, which has 3 sig figs. So my answer should be 3 sig figs. So therefore, this answer would be 0.000830 would be the correct answer. Or if you want to put this in the scientific notation, you can, and that would be -4 moles of cobalt. So try the next one on your own and then come back to check the key, and then we'll go on to the next one. Here is the key. The next one asks how much atoms of neon are present in 0.099 moles of neon. So your starting value is 0.099 moles of neon, and you want to do some calculations so that you're left with atoms of neon. So same thing. The relationship between moles and the atoms are as follows. Either you have 1 mole of neon on top and the Avogadro number on the bottom, Or you could have one at the Avogadro number on top, and then you have 1 mole of neon on the bottom. Okay, so which one would you utilize? The second one. The reason why we use the second one is so that we can cancel out the mole in our calculation. Mole of neon and the rest. Right? And then let's go ahead and calculate this out. The moles cancel out. So we press 0.099 times, and then close the parentheses, and then we want to include this 6.022 times 10 to the 23. Close it, open and then close. Press enter. Okay, took care of everything on top, and now we need to take care of bottom. Divided by just 1. That's what I get, which would be 5.9616178 times 10 to the 22, based on what the calculation said. But there's 2 sig figs here, so I should end up with 2 sig figs, and that's 5.96 times 10 to the 22 atoms of neon. So that means that's how many atoms there are for every 0.099 mole of neon. Okay? And this applies not just for atoms, but we could apply this as molecule. Even if this neon has been crossed out and say and the atoms are crossed out, and you say molecules of, H2O present in moles of H2O, you should end up with the same answer. It's just the word atom will change to molecules. Okay?